Welcome to this podcast on specific immunity. Specific immunity is acquired. At one time we do not have it, and then we acquire it. It is also adaptive. It allows us to adapt to exposure to particular disease-causing agents. And just before we go into it in more detail, we need to think about antigens and antibodies. Let's think about antigens first. Now, an antigen is anything that the body recognizes as being foreign. So the immune system is able to differentiate between that which is part of the self, the body's own tissues. But then if some other life form gets in, like a bacteria or a virus, although we could argue whether a virus is a life form, but when something foreign gets in, the immune system recognizes it as being foreign, and that is what an antigen is. An antigen is something the immune system recognizes as being not part of the self. It is foreign, and it will have an antigenic effect. And the reason that antigens have an antigenic effect is that on the surface of their cell membranes, on the surface of the cell, or if it's a virus, the proteins which form the outer coat of the virus, they act as epitopes. And we can see this on the diagram on page 356 if you've got the white book. So the epitopes are the actual molecules that the immune system recognizes as being foreign on the surface of an antigen. The actual antigenic molecules are the epitopes. And these are usually specific proteins. Now, proteins are very complex structures, and they form what is called an architecture. They have a particular shape. They fold together to form physical three-dimensional shapes. And the immune system is very clever and can tell the difference between the body's own protein shapes and foreign protein shapes. So the foreign protein shapes are the epitopes that allow the immune system to recognize that something is not part of itself. And when this happens, the immune system responds by producing immune proteins. And immune proteins are called antibodies. They're sometimes called the little soldiers of the immune system. They're the ones that do most of the work. Antibodies are immunoglobulin proteins. And antibodies are based, it's different forms, but antibodies are based on a Y-shaped molecule that we see on page 365 in the white book. They have a body and they have two arms. So antibodies is a good name. They've got a body and two arms just the same as us. And there's variable regions on the end of the antibodies. And these variable regions are massively complicated molecular structures because they are made to be the exact reciprocal shape of the epitope. And the arms of the antibodies can move. So what I tend to think of the variable regions on the end of the antibody as being the hands of the antibody. They can grab onto things and hold on to things. And once they grab onto an epitope, they'll hold on to it. And that's important because it means that an antibody, as we see on page 364, it means an antibody can bind onto two epitopes. Now, the way to think about it is, if you were at a party or something, and there was two girls you liked the look of, you could grab one with one hand, and you could grab one with the other hand. It might not be appropriate. You could do it. You could grab two because you've got two hands. And that would hold the three of you together because you're holding on to two of them. And it's much the same. The antibody can grab onto two antigens and hold them together. But then, of course, if there's more antibodies, you can end up with a big clump of antigens all bound together. So the antibodies can bind together or agglutinate or clump together large collections of antigens. And once there's a large collection of antigens all clumped together, it's relatively easy for some large phagocyte like a macrophage to come on and gobble the lot up, just eat them all, phagocytose them all together. So it has been said that antibodies prepare the food for the phagocyte's table. It's a bit like if I wanted you to eat a tube of Smarties. If I put one here and one in a town 2 miles away and one downstairs and one in the next door neighbour's house and they're all spread all over the place, then it would take you a long time to go round and collect them. and eat them. And it's just the same for the macrophages and the monocytes and the neutrophils, the phagocytic cells. If the antigens were spread out all over the place and they could only eat one at a time, it would take a while for them to combat the infection. However, if I give you the entire tube of Smarties all together in one tube, then you could consume them in a relatively short period of time. And it's exactly the same situation with the agglutinization of antigenic material by the antibodies. The fact that they're agglutinated and all in one place means that a big phagocytic cell can come along and eat the lot all at once, and do so very efficiently. Nice saying that, I like that one. The antibodies prepare the food for the phagocytes table. Now, as well as that, antibodies work another way. They can precipitate soluble antigens. It's much the same, really. If there's antigens in solution, tetanus is bad for this, tetanus toxin, for example. They can float round in the solution, grab hold of all the antigens and precipitate them out. Again, it's kind of bringing them all together, really. It is kind of an agglutination effect. And antibodies can also neutralize some antigens. Some antigens have toxic sites, and antibodies can sit over them and stop them from doing any harm. It's a bit like putting a sheath over a needle or a scabbard over a sword. It makes it non-toxic. And some antibodies actually work by lysis. They will cause antigenic cell membranes to rupture, and that will kill the cell. But the basic point is that the antibodies are specific to a particular antigen, and they are immune proteins. Now, having said that, let's get an overview of the process of immunity. As we've said before, immunity can be divided into innate, that is non-specific, or acquired, specific, adaptive, which is what we're talking about today. Now, acquired immunity itself can be divided into two basic forms. It can be active immunity, or it can be passive immunity. That is active specific acquired immunity, or passive specific acquired immunity. Now, let's do passive first. In passive immunity, a person becomes immune to something because they've been given antibodies which have been produced by someone else. So they enjoy immunity, but they have not had to bother making the antibodies themselves. And we can do this by giving injections of immune globulins. We used to do this when we gave a gamma globulin, although we do it much less now because we have active vaccinations for hepatitis. But physiologically, this happens transplacentally. So antibodies are able to diffuse across the placental membrane from mother to baby. And this is absolutely vital because it means when baby is born, baby will have the antibodies in their blood which mum has in her blood. Baby did not make the antibodies, baby has received them from the mother. And if this wasn't the case, as soon as a child was born and came out into our world with lots of potential infective microorganisms, they would have no resistance to these diseases at all, would get these diseases very quickly, and presumably all babies would die within a few days of birth from infectious complications. But they don't because they enjoy immunity from their mothers. And as well as that, in the first day or two of life, babies get colostrum from their mothers, the thick serum-y type fluid that comes from the breasts before milk proper comes out. And this is absolutely crammed full of antibodies, and it's absolutely vital that that baby gets this to drink because it really boosts their immune system. And there are further antibodies in breast milk as well from the mother. So that would passive immunity. It's still acquired, but it's a passive form of acquired immunity. Now, the other form of acquired adaptive immunity is active. And active is where the individuals have made the antibodies themselves. They make their own antibodies. So if someone has suffered from a disease, that means, an infectious disease, that means they've been exposed to the antigens, the causative antigenic organisms of that disease. By definition, they've been exposed to it because they've suffered from the disease. That means the immune system has been exposed to these specific antigens and epitopes, and the immune system will have responded by making antibodies. So the person enjoys immunity, they have the antibodies because they've made the antibodies themselves after exposure to a specific disease-causing agent. Now, that would have been, if someone's had the symptoms of a disease, we would call that symptomatic disease. But occasionally people might get exposed to an antigenic organism and not develop symptoms of the disease, but they've still been exposed to it. That would be asymptomatic disease. But the point is the same. They have become immune because they have been exposed to the causative organism. And the principle here is the same with immunization. When we give injections to immunize someone, we are actually giving the antigens. We're giving them antigens that stimulate their immune system into producing antibodies. So some immunizations are living organisms, although they're attenuated, they're weakened. So the individual's immune system is exposed to the living but weakened organisms. Some organisms are dead or broken up, but it doesn't matter, because even if the organisms, for some immunizations, even if the organism's dead and broken up, it still contains the antigens and the epitopes. They will still be recognized as foreign by the body's own immune system. The body will still respond by producing antibodies. And then, if the individual is subsequently exposed to the live organism, to the live antigen, it will already have antibodies to those specific epitopes and be able to mount an immune response rapidly to the organism. And the place to start thinking about this is with the lymphocytes. Now, do you remember before we said that lymphocytes can be described as large or small? And the large lymphocytes were the NK, the natural killer cells. But in the specific immune response, we're thinking about the small lymphocytes. And the small lymphocytes can be described as B or T lymphocytes. And the reason for this is that the B lymphocytes mature in the bone marrow, and the T lymphocytes mature in the thymus gland behind the sternum. Now, it's the B lymphocytes that are the actual factories of the antibodies. The B lymphocytes produce the antibodies. And the T lymphocytes are in three forms. There are T helper lymphocytes. Now, the T helper lymphocytes recognize the presence of antigens and respond by producing cytokines. Now, a cytokine is an intracellular hormone. It is a hormone passed from one cell to another, sending messages. And there's a diagram of this on page 360 in the White Book. And what the T helper cells do is they help the immune system to work. So T helper cells will release these cellular chemical messengers called cytokines. And they will stimulate neutrophils, monocytes, mast cells. They will stimulate different cells in the immune system. But the main thing that they do is that they stimulate the B cells to produce the antibodies. So without the T helper cells, the B cells will not be helped to produce the antibodies. And this is why HIV causes acquired immunodeficiency syndrome, because it's the T helper cells which are attacked by the HIV virus, and the number of T helper cells goes down. So AIDS is affecting the T helper cells. Now, when the immune system has combated an infection, it's necessary to suppress the immune response, and that's carried out by the T suppressor cells. So the T suppressor cells limit the extent of the immune system, or the immune activity. And there's a third type of cell called T cytotoxic cells, and these will kill whole cells which are infected, or they will, interestingly, they'll probably kill cancer cells as well, because the area of cancer and immunity is another one which is often, or can be, tied together. So we have the lymphocytes, the B and T cells, and it's the B cells which are producing the antibodies, but the T lymphocytes are stimulating other relevant immune cells like monocytes and neutrophils, which are also very important. And I think the last thing we might do on this podcast is look at the primary and secondary response in in specific acquired adaptive immunity. Now, in a primary response occurs when the body has not been previously exposed to an antigen. It is a new infection. And what happens in this situation is it takes about 7 to 10 days for the body to mount a full antibody response. It takes some time, because a process has to be gone through. And if you've got the white book, this is illustrated on, where is it? No, yeah, there's a good illustration of this on page 362, if you've got the white physiology notes book. But if not, don't worry, just listen. An antigen gets into the body. Now, the antigens are recognized as being foreign, first of all by the B cells, and this is true for B and T cells. So what happens is that there's millions of different types of antigens, but for every antigen in the world there is a lymphocyte which has an antibody on its surface which is a reciprocal shape to that antigen. This means that in your circulatory system at the moment there are millions and millions of lymphocytes circulating around, and on the surface of their cell membranes are millions and millions and millions of different shaped antibodies. Quite amazing. And when you're exposed to a particular antigen, the only lymphocyte which will bind to that antigen is one which is expressing an antibody which is able to bind onto that antigen, one with a reciprocal shaped antibody on its surface. So eventually the antigen will bind onto its specific antibody. And when this happens, that stimulates the lymphocyte which is expressing the antibody to divide. That lymphocyte will start to divide, and when it divides it will produce exact copies of itself expressing the same antibody as itself, and this is called clonal expansion. So this single lymphocyte will divide and produce millions and millions of further lymphocytes, and this process is called clonal expansion. It's a clonal expansion because the lymphocytes that are being produced are clones of the original one. The original lymphocyte divides into two forms. Now, the first form are called the memory lymphocytes, and there won't be a huge number of these formed, quite a few, but not massive numbers. And these lymphocytes are called memory cells. They have the same genetics as the original lymphocyte, therefore they will express the same antibody as the original lymphocyte, and these can live on for months or years. So they're the memory cells. But clonal expansion will also give rise to another cell line, and these are the effector cells. And these are called plasma cells. And these will be generated by untold millions of them. Millions and millions of them will be generated. And they are the effector cells. So there'll be millions and millions of new T cells to stimulate millions and millions of new B cells to produce untold numbers of antibodies or immune proteins. So, when a new antigenic organism is introduced into the body, it will divide rapidly, and that will make the individual sick. You'll be unwell because of the proliferation of the foreign infecting organism, whether it's a bacteria or a virus. Now, that'll make you sick. And then, for the first day or two of the illness, there's going to be more division of invading organisms. It's an arms race, really. There's going to be more invading organisms produced than the body's able to mount an immune response initially, so that you're going to get sick. But then, the reason you start getting better is that the immune system catches up, makes enough antibodies to deal with the infecting organisms, and then we start to get better. That's the way it works. So you're ill for a few days until the immune system catches up, makes the antibodies get rid of the infecting virus or whatever it is, and then you start to feel better. Unless, of course, the infection is overwhelming, and causes death before we have time to mount an adequate immune response. That is always a possibility. But thankfully, most times we start feeling better because we're making enough antibodies. And then the effector cells from the clonal expansion will die after a few days. These are called plasma cells, these effector cells, and you produce millions and millions of them. So like when you have a viral infection, you'll get a lymphocytosis, an increase in the number of lymphocytes. And that's how you can tell someone's got a viral infection very often, that there'll be an increase in the number of lymphocytes. But these effector cells will die after they've done their job, and the antibodies will have eradicated the infection. But do you remember there'll still be some memory cells left floating around, and these memory cells can be there for years. Relatively small number of them, but they'll still be there. Now, this means that if we are subsequently exposed to the same organism, we already have a population group of memory cells. And in the same way, the infecting organism will select the antibody that is reciprocal to it. It will select the antibody on the surface of the memory cells. But this time we have a small population of memory cells rather than just an individual cell. And this population of memory cells are able to divide up very, very quickly. And again, they'll divide into effector cells and produce a large population of clonal plasma cells very quickly that will make lots and lots of antibodies. And they'll also produce more memory cells. So this means that if we're exposed to an organism again, we can mount the immune response much more quickly. And usually, the body can mount the immune response so quickly that we don't even know we've been exposed to the organism again, because we just get rid of it. We don't actually get clinical features most times. So, the primary immune response takes 7 to 10 days, and it occurs when we have not been exposed to the organism before. The secondary response takes place much more quickly, and will take place when we have been exposed to the organism before, because we have a population of memory cells, and we can get rid of the infection before it even causes clinical features, usually. And again, this is the same principle with vaccination. If we vaccinate someone, we will produce a population of memory cells, and hopefully that means that when someone is exposed to the organism which might cause a disease, they don't need to mount a primary response because they've already generated a population of memory cells, and we can get a secondary response straight away, massive amounts of antibodies produced, and that will mean that the disease is suffered from in a much milder form, a much shorter duration of illness, or hopefully not even get clinical features at all.